Okay, in the last video we started talking about doing integrals in cylindrical coordinates. So at the top of the board here, I've just sort of summarized what we said there. If I'm given a triple integral of a function of x, y, and z, and I want to switch to doing it in cylindrical coordinates, I'll obviously need to figure out what my limits are, and that will vary by the problem. But the integrand here switches to f of r cosine theta, y becomes r sine theta, z stays as z, and then dv becomes r dz dr d theta. So just like with polar coordinates, I get this extra factor of r, and so my new integrand becomes the original integrand expressed in terms of cylindrical coordinates multiplied by r. So I want to just try an example. Let's say I wanted to do the triple integral over e of x squared dv. And we're going to say e is the region in between the paraboloid z equals x squared plus y squared and z equals 5. So we're just looking at a portion of the paraboloid like so. This up here would be the plane z equals 5. And pretty clearly if I project that onto the xy plane, I'm just getting that circle and its interior, which would be this disk. Notice that disk is the disk where x squared plus y squared is equal to 5, because it's where the bottom surface and the top surface meet. So do be careful. That means that the region D over which I'm integrating in the xy plane is a circle of radius root 5, not 5. Okay. All right, so if I wanted to set up this integral, okay, I know my x squared is going to become r squared cosine squared theta. dv is going to become r dz dr d theta. I'm almost always going to set things up in this order. I don't have to, but it's very convenient for me to think of z as just the top and the bottom, and then r and theta are my polar coordinates that I'm used to working with in the xy plane. So for our z values, we're going from the bottom surface, which was z equals x squared plus y squared, that becomes r squared, to the top surface, which is just 5. Okay. And then describing this disk in polar coordinates, which are part of the cylindrical coordinates, r is varying from 0 to root 5, and theta is going from 0 to 2 pi. Okay, so we've got our integral nicely set up. Now let's just do it. So, integral 0 to 2 pi, integral 0 to root 5, integral r squared to 5. This is going to become r cubed cosine squared theta dz dr d theta. So when I integrate with respect to z, an antiderivative here will just be all of that times z. So we'll have the integral from 0 to 2 pi, integral 0 to root 5. It's going to become z times r cubed cosine squared theta, evaluated between 5 and r squared, and then we still have to integrate dr and d theta. So I'm plugging in the 5 and the r squared for z. Okay. So that's going to become the integral from 0 to 2 pi, integral from 0 to root 5 of 5r cubed cosine squared theta minus r squared times r cubed, which would be r to the 5th times cosine squared theta. And that all we're going to integrate dr d theta. So let me clear some space here. So it's the integral from 0 to 2 pi, integral from 0 to root 5. I'm just going to copy it up here, 5r cubed cosine squared theta minus r to the 5th cosine squared theta dr d theta. Now I can completely erase the rest of the board. Okay, so taking an antiderivative with respect to r, integral from 0 to 2 pi, I'm going to get 5r to the 4th over 4 times cosine squared theta minus r to the 6th over 6 times cosine squared theta. That's evaluated between 0 and root 5, and then we have to integrate with respect to theta. So, integral 0 to 2 pi of, when I plug in root 5 to the 4th, well, let's see, root 5 times root 5 is 5. So the other two root 5s are going to give me another 5. So I'm going to have 5 times 5. That's 4 factors of root 5. So that's 25 times 5 is 125 fourths cosine squared theta, minus now r to the 6th. So remember, each pair of root 5s is giving me a 5. So this is going to be a 5 times a 5 times a 5. So that's 125 sixths cosine squared theta, minus, when I plug in 0, I do actually just get 0. So we're just going to have to integrate this with respect to theta. I think I'm going to go ahead and factor out the cosine squared theta and just find a common denominator here. Looks like I could use a common denominator of 12. So this would become 375 twelfths minus 250 twelfths, and then d theta. So all of that is just 125 twelfths. I'm going to factor that out. So I've got 125 twelfths integral 0 to 2 pi cosine squared theta d theta. Once again, we've got an even power of cosine. I'm going to derive this formula one more time. I probably won't derive it every time in the future because I have accidentally memorized it by using it so often. Okay, I would encourage you to memorize it or to derive it as often as you need to until you accidentally memorize it. That way, if you forget it, sometimes we accidentally forget something after we've accidentally memorized it, you'll remember how to get it back. So cosine 2 theta is cosine squared theta minus sine squared theta. So that's cosine squared theta minus 1 minus cosine squared theta. Distributing the negative makes this one positive, so that's 2 cosine squared theta minus 1. That was still equal to cosine 2 theta. So I'm just going to add over the 1 and divide by 2. So cosine squared theta is cosine 2 theta plus 1 all over 2. So I'm going to rewrite this that way. I'm going to go ahead and just pull the 2 in the denominator out right from the get-go. So this is going to become 125 24ths because I've pulled out the 2. Integral from 0 to 2 pi cosine 2 theta plus 1 d theta. And now it's just a quick u sub. Let u equal 2 theta. du is 2 d theta. One of the trickiest things about these even powers of sines and cosines is just keeping track of all the factors of 2. Because there's a 2 in the denominator here. There's a 2 that we have to introduce when we do our u substitution. And it's easy to look and say, oh, there's a 2. I must have already written it. But sometimes there are lots of 2's. Okay, so now this becomes 125/48 integral from 0 to 4 pi. These become the u values here. And then it's just cosine of u plus 1 du. So I'm going to bump up to here. 125/48. Antiderivative is going to be sine of u plus u. And we're evaluating that between 4 pi and 0. So 125/48 times sine of 4 pi is 0, plus 4 pi is 4 pi, minus sine of 0 is 0, plus 0 is 0. And I can cancel a 4 with that 48, so I'm going to get 125 pi all over 12. That's the value of this particular integral.